The one-shot instruction. Welcome back. This is where we left it in the last video lab discussion, and you can't tell it. Well, actually you can, but it's not real obvious that we are online. So looking at this image, how can you tell that we're online and in the run mode? The green or the highlight here on the power rails. The reason it is not obvious is because we removed a couple menus, a couple toolbars, so we could get more vertical space with our logic. You might think you could go to Window, Arrange, and hit OK to default. That's not going to do it because it's the default configuration but not the default toolbars. So we'll go back and we'll do default toolbars. See, now we're back to the actual default, but notice now that we have the default toolbars, but our ladder view disappears in the window. So we can go one more time to Window, Arrange, Default Project. Now we're right back to where we were before. Now the reason that we eliminated these toolbars was so we could see more. So I'm going to geezer this down, and you see if I geezer it down enough where you can see all of the rungs, you still can't see them all. It pretty much becomes useless. So this is always a challenge, how to arrange your view to see specifically what you're interested in. So I'm going to zoom back in with the geezer button, and this is the logic up here that we're actually running. We have the classic start-stop circuit to do a system enable. In other words, we seal in this condition B330 with B330. We seal it in. Once you hit the start push button, it stays until you hit the stop push button, or you lose power, or you leave the run mode. Then we have three more rungs of basically the same logic, except we've had a condition that the system enabled bit beyond with these three true if ons. And from these four rungs, we run these three conveyors manually. We got an overall enable and stop. This is a start system which enables you, so really it should be enable system push button if you run it to be really picky, because we're doing system enabled. All the rest of the code that we did was a little exercise early on for timers, to give you wet your feet a little for timers. All of this logic right here simulates push buttons. So we could single click, single toggle, it would go on and right back off after hundredths of a second. We set our preset at 200 with a time base of a thousandths of a second, but it could have been less. I like 200 because it allows you to see a little flicker when you toggle it. You just saw it appear, just momentarily. Always keep in mind that the refresh rate on your computer screen, it's not going to catch things even if they were there long enough for you to see them. So if we were to bump this timer down to 100 milliseconds or a tenth of a second and do the same thing, oh, we saw it. If you see it 2 times in a row, then you're probably good. We'll go down to 50. And try that again. Oh, you still saw it. Try 25. Now we're really pressing it. Every once in a while you'll catch a flicker just because of the timing issue of when you did it and when the refresh rate was on your screen. I'll bump this back up to 200 and we're going to move on. Next up on the projects that you did was the one-shot instruction. This instruction is incredibly important. It's an extremely powerful instruction that gives you all kinds of benefits. We're going to beat it to death in our lab projects. Before we leave this project, you could have opened yours, Micrologix 1400 Challenge 1 Part 2, and then saved it, save as, and save it. That way we don't accidentally overwrite. You notice I saved this first as the former name, then I saved it again as the new name. Now I'm going to, and if I'm going to go offline with it, remember I did this all online. So if I just go offline and I don't save anything, we're not going to have a file there with that name in the offline mode unless we open it up in the offline mode. See, right now I've not saved this. First, save it along with all the data, and then I'll clean it up offline. Now I'm going to go offline. Now I'm going to delete all the logic. I just put my cursor on rung 0 and keep hitting delete until they're gone. And just to clean it up even more, I'm going to go to database, delete database. That doesn't delete the files. That only deletes the names that we put on the files. See, we still have 10 words in B3. The first rung I had you put in was a Troubleshooting, OneShot, and an OTE. What you might have noticed when you were doing the OneShot was that you had 3 of them up here. OneShot, OneShot rising, OneShot falling. OneShot is a OneShot rising, but it's more general. OneShot rising, what that means is that that instruction is going to be true on the rising edge of the false to true transition, whereas this OneShot will be true on the falling edge of the true to false transition. You can actually get everything done that you need with the basic OneShot instruction. I clicked on it again and add another one, and we do have to give it a unique memory location, and I picked the easiest, and that is B3/0. I called it hammer because I'm going with the idea of a one-shot firearm. I'm going to geyser this up just in case you need reminded. I:0.0/0, B3:0/0, and O:0.0/0 are not memory locations. They are pointers, they're tag name, they're designations that make sense to us that point to the actual memory locations, which are numerical, but wouldn't make any sense to us. Trigger, hammer, and round, as in the trigger on a firearm, the hammer on a firearm, and the round or cartridge, they are aliases for I:0.0/0, B3:0/0, and O:0.0/0. They are aliases for those pointers that point to memory locations. It's easier, though, to program with an alias typically, because you may not remember what input address you assigned to the trigger. So if I were to start a new rung, click here, and I'm going to hit a different instruction. If I type in trigger, I get the pointer with it. If you went through and you had 10 photo eyes, 1 PE or 2 PE, or if you did it the other way around, PE1, PE2, 3 through PE10, you don't have to remember the actual input type pointer that points to a memory location. You just need to remember the symbol. You will lose symbols uploading and downloading, so they're not permanent, but they are always unique to that memory location. So I'll delete that. So I had you download and go online in the run mode with all the switches off. Turn them off before you download. Turn the switches off on your demo. I also had you open some data files and lock them on top. You always want to lock them on top before you change the shape. I'm sure you'll learn the hard way. If you try to collapse them down as I have here, then lock them on top, they pop back to the default shape. I only had you open B3 and the output. However, I've got all 3 of them here represented. So you got the input, the OneShot memory location here, B30. So here's input 0, B30, and output 0. So you can follow the change in state of these bits as we exercise them. So I had you repeatedly toggle on and off the input while watching B30 and output 0. They're highlighted in blue right now. Before I go along, notice that these bits are on. That's because that's data table carnage. Those were left on from the previous lab. Remember, I told you if you delete logic, especially online, if whatever the last thing was those bits heard, that's the state they stay in. So I just turned those all off so it looks nice and clean. So I had you toggle input 0 on and off. Okay, notice that I have input 0 is on right here, and the output is off. Now you're never going to see this output go on right here. We'll go ahead and highlight those 3 to keep them easily in focus. So I'm going to turn off input 0. Notice that B300 goes off with it. So you'll notice in doing this lab that B300 follows the state of input 0 exactly. If I were to add another condition in front on either side of trigger, then you would not see this bit go on and off with this bit unless both of these conditions were true. But right now we're working with a real simple one-shot. Everything to the left of the one-shot instruction has to be true for this instruction to execute. And when this instruction executes the one-shot, everything to the right of it but to the left of the output, so anything in between here, conditions, they all have to be true during the one program scan when this is true, or you're not going to execute this output type instruction. Now we're going to beat that idea to death. So do you think that the memory location that output 0 is pointing to is going on off with the memory location that input 0 is pointing to? Since the question was, do you think, you could have answered anything. Well, I'm going to say yes because I know that it was, because I'm intimately familiar with the one-shot instruction. How would you use the instructions that you have learned to prove whether or not output 0 is reacting to the logic? In other words, you're looking at your output right here, and you can look at it on your demo. I'm turning it on and off, and I'm not seeing the output going on and off. So how could you prove that that output was actually going on every time this instruction went from false to true? Now remember, this instruction represents everything between the left power rail and the one-shot instruction. This could be a dozen instructions. And when they're all true, that's the same as this one instruction being true. That's what we're demonstrating here, is we have really three areas of interest here. Whatever is to the left of the one-shot, whatever is to the right, and the one-shot itself. What it's actually executing really is no importance to us. We're only talking about the one-shot instruction. So I had you add some logic. I added something I refer to as a bit trap. Added a latch instruction in parallel with the OTE. Now you know that the OTE has a false and a true execution. So when this rung 0 is true, the OTE says, hey, output 0, you're on. If the rung is false, it says, hey, output 0, you're off. The one-shot instruction is only true for one program scan until you reset everything on the left side of the instruction. So it's only going to turn on output 0 for one program scan. Well, that's less than 1,000th of a second. If it's anything that has to move, even a solenoid valve, it's not going to move. So how do you know that that bit actually turned on? We add a latch in parallel with it, and I'm going to hit the trigger now real fast. So fast that you didn't even see it come on the screen. That was pretty quick. But notice that it's latched. When you look at this rung of logic, you have to say to yourself, this rung was true. Otherwise, that bit would not be latched. So I latched on input 1. When I look over at my demo, I see 1 on. The problem is that to easily repeat execute it, you have to go in and toggle it off. And then you can do it again. Instead, there's several ways that you could add a reset. One, you notice I'm going to drag down this memory location. That's not what I want to use. I want to use a different one. I'm not going to bother putting a memory location on it. Then I'm going to drag this memory location down there. Then I'm going to finalize it. Now I'm going to hit the trigger. I know that that rung went true and the one-shot did execute, otherwise that would not be latched. Then I'm going to press input 1 and it's unlatched. Could have put input 0 down here and put true if off. So when the button's off, it unlatches it. When it's on, it latches it. We're just trying to demonstrate something to you here on this one-shot instruction. Okay, you have used the OTL and OTU instructions. Explain how these edits will prove whether or not the tag name output 0 is toggling on off. That's real simple. If output 1 is on, the only place that is turned on anywhere in the program is in rung 0. Rung 0 had to be true, otherwise it would have never come on and be latched. A question in the manual: with output 0 and output 1 in parallel, what does the state of output 1 tell you about output 0 when the trigger was pressed and released? That the rung was true for that one scan. Also, while maintaining the memory location controlled by trigger, does the logic indicate that bit B300 is in the on state? No, it doesn't. You'll never see that instruction go true, B300. It does not display the true-false state or the on-off state. Looking at the B3 data file, does it indicate that B300 is in the on state? Yes, it does. If I hold down the input and you look at B3 0 0, you see that it's in the on state right now. But when you look at the instruction, you don't see true, false, on, off, anything. Once you learn the OneShot well, if you see that everything to the left is true, then you know that bit is on. You will not find an exception to that. Paraphrase what you learned earlier about every instruction to the left versus every instruction to the far right. We're talking not including the OneShot. So previous logic, everything to the left side of the rung is true or false. Everything to the right end of the rung is on or off. Do the graphical highlights of instructions to the left indicate on off? No. They indicate true false. You can interpret the bit memory as on off based on whether or not it was a true if on, true if off instruction. But the highlights on the instructions to the left do not indicate on off. They indicate true false. Do the graphical highlights of the instructions to the right indicate true false? No, they don't. They indicate on off. If the data file display shows that B300 is in the on state, then what does the lack of highlight on the ONS instruction that is reading, writing to B300 indicate? It indicates that you can't look at the instruction and determine whether the instruction is true or false just by looking at it. And the reason is because that ONS instruction is a read and a write instruction. It's a compound instruction. So you could treat it like this. Input 0, trigger. If it's false, meaning the trigger's off, therefore that true if on is false. So if the rung out from that first instruction is false, then the writes a 0 to its memory location. That's an actual output. And then it declares the OneShot as false. So it writes a 0 and declares it as false, and the false out of the OneShot then makes the OTE that addresses output 0 execute its false execution, and it sets output 0 to 0. The latch instruction, the OTL, it does not have a false execution, so it does nothing. Next time around, let's say the trigger's pulled. And so that makes that instruction true. Because the instruction is true, the true execution of the OneShot is to go read the bit, B30. And if that bit is off, then it sets the bit to 1, declares instruction as true, executes the true execution of the OTE for round or output 0, and executes the OTL for output 1. Next time around, trigger's still on, it's still true. The OneShot in the true in from the previous instruction reads the bit in memory. If it's off, which it isn't because remember it's set it to 1 on the last scan. If it's on, then it declares this instruction is false, and then the OTE and the OTL execute their false execution, except the OTL does not have a false execution. So you can see if you turn on the trigger, it'll turn on output 0 for one program scan, less than 1,000th of a second. Later, it's going to come through, trigger's still true, so the OneShot's going to be false, and output 0 will set that back to 0. It's that simple. That's what makes the OneShot instruction so unique. It is a read-write instruction. It reads the memory location, and based on the true-false nature of everything to the left, it has a true to false execution. And it has its own bit in memory to remember that it was true or false on the last program scan. Okay, so I had you add a little more logic. We redid our logic a little bit. I added an instruction, a true-if-on, between the OneShot and the output instruction. And I used the memory location pointed to by input 1, which was our reset. Notice I have input 2 now as the reset to reset the trap bit. And we're going to demonstrate the relationship between true-false on the left and true-false on the right of the OneShot. So I had you press and hold the trigger, and you look at B3, you see B31 or B300 is in the 1 state. Does the state of B30 follow the state of input 0? Yes, it does. Did output energize at all? Now, the only reason you can answer this is because the hole in the target's not on, right? So, did output 0 energize at all? No. How do you know that? Because output 1 is not on. Next, I had you press and maintain the trigger, and then press and hold the safety. So I'm holding the trigger on. Now I'm going to hold the safety on. Does the state of B30 follow the state of input 0? You can see that down below. Yes, it does. Did output 00 energize at all? No. How do you know that? Again, the hole in the target or the latched memory location output 01 did not come on. The question again was, repeating it, does the state of B30 follow the state of input 0? Yes. Did the output 0 energize at all? No. How do you know that? Because the bit trap did not capture the true state of the wrong. There was no true state. Whatever is going on to the left, it was not true. Now, I didn't tell you to release it, so I'm going to hold it down again myself. I'll just flip it on. That's the nice thing about using these universal field device simulators is you can have momentary or maintained. So I've got it turned on. Does the rung appear to be true? Well, if we hold on to safety, I would say yes, it appears to be true. Does output 0 appear to be on or to have been on? No. The OneShot is only true for one scan, which might be as short as 1 microsecond. Would you see the actual output or its bit in memory go on? No. You'd never see it. How do you know whether or not output 0 energized? The bit trap. That's the whole purpose of it. Remember, the bit trap, our OTL there in parallel with the OTE, it serves no purpose to the machine or the process. You put it there, I had you put it there to demonstrate that's the only way that you can troubleshoot this type of logic and see whether or not the rung was ever in a totally true state from end to end, and that if it ever turned on output 0, because looking at it right now, you don't know what order those inputs went on. In this case, I turned on the trigger first, so I'm going to turn off the safety, turn off the trigger. I'm going to turn on the trigger first, then the safety. But looking at it, you wouldn't know that. See, now we're going to reverse it. So we're going to turn them both off. We're going to turn on the safety. Does the state of B30 follow the state of input 1? No. B30, it reflects that something to the left was true, not something to the right. Did output 0 energize at all? No. How do we know that? The bit trap, right? While maintaining the safety, press and hold the trigger input 0. Does the state of B30 follow the state of input 0? Yes, it will always do that. Did output 0 energize? Yes. And how do we know that? Bit trap. The address or memory location addressed by that OTL named bit trap, it's on. So we know that that rung was true at one point. Now the whole reason for showing you this sequence is when you're interpreting logic that's using the OneShot, in most cases you won't have anything between the OneShot and the output. So you're only analyzing what's to the left to see if it's true or was ever true to fire the round. But in some cases, and I do it quite often myself, I have a situation where I want things to occur in a certain order. Well, guess which one has to be true first before the other one's true? What's to the right of the OneShot has to be true before everything to the left, but they could be true simultaneously. Now that's pretty hard to do. The safety would be analogous to the safety on a firearm. If the safety's not off, and I know that's a true if on, not true if off, but, and I suppose just for grins we could change that if you like. Right click, change instruction type. Now the safety's off, and if we hit the trigger, it fires, right? We got a hole in the target. However, normally the safety's going to be on, pull the trigger, nothing fires. So that's all a matter of semantics, whether you want the safety to be on or not. So maybe I should change that to safe condition is on, which would mean that the machine is safe. So when you pull the trigger, it drops the hammer and fires a round. You can interpret that any way that you want. And the last question in there was, does the state of B30 follow the state of input 0? It's always going to follow. Now if we had more conditions in here, as if we added something else. Now if you watch input 0 and B30 down here, see, it doesn't follow, because we'd have to have 1 and 3. Both of them have to be true. Now it doesn't make any difference what order they go true. So input 0 is true, watch B300. Now we'll do input 3 and then input 1. See, it doesn't make any difference what order they go on. But practically speaking, everything to the right, in this case, whatever conditions, permissives, instructions are to the right of the OneShot, they have to be true when the left side goes true in order to get a true out all the way through to the output type instructions. For the practical example, you could have opened up a couple different previous projects. I'm going to open up one and work with that to complete the practical example for a OneShot. This is our previous practical example using latch and unlatch. We're going to work with this. And if you remember what this logic did, I push the stop push button here. It stops, push the start push button, the motor runs, and we've got 1 PE blocked, and then if we block 2 PE, before we clear 1 PE, it declares that the carton's too long and we get a fault. Remove the carton, hit the stop button to reset it. However, if we hit 1 PE, in other words, we block the optical path of photo I1, and then clear it before we block the optical path of photo I2, no fault is declared and the carton goes on its merry way. However, if we happen to block 1 PE and before it clears 1 PE it hits 2 PE's optical path, we get a size fault. Okay, now it is possible that when this is running, we could block optical path 1, clear it, and while we're blocking 2, some Yahoo comes by and throws his fingers in there and makes it fault and stop, and you come and look and it's not blocking both photo eyes simultaneously, so you're wondering what's going on. Well, there is a way to prevent one of the scenarios of happy fingers in the photo eyes. I'm going to add a OneShot instruction and move some things around. I'll move this over here and this over here. Now before we had 1 PE and 2 PE, they were ANDed. So if you have 1 PE and 2 PE, then we declare a size fault. Okay? And it really doesn't matter what order they were in the rung. Now it does matter because we're going to do a timing thing. We're going to use B3/0 and we're going to call it OneShot 0. Okay, first thing we'll do is test normal function. We have a size fault, so we've got to do the stop first, and I'll also turn off 2 PE so we're starting clean. So we start the conveyor's running, so we should hit 1 PE, then clear, then hit 2 PE, then clear. So it still works the same. And again, it does still function correctly. If we start it, and we have 1 PE, clears, block 2 PE, clears, everything's fine. But let's say that 1 PE clear, and while still in 2 PE, somebody blocks 1 PE with their fingers. Notice nothing happens, because this demands that one PE already be blocked when 2 PE is blocked to say that there's a size fault. Now that does not protect it the other way around, where we'll clear it, where we have the situation where 1 PE is blocked and somebody reaches in and flags 2 PE before it actually gets to 2 PE. So it can block one of the faults, or I should say false triggers, but not both.